Okay, welcome everyone. I think we can start. Let me share my iPad. Um, okay. Uh, so maybe before we begin, like as usual, a couple of quick announcements. One major announcement. So tutorial 2, which was supposed to be tomorrow, we are going to shift it to next week. So I'm sorry for the last minute notice, but I thought it would be better if we do tutorial 2 after we cover few more algorithms in today's lecture, Monday and Thursday, so that it becomes more useful and you can learn how to use all these algorithms that you're going to learn in the next few lectures in the tutorial. So tutorial 2 is moved to next Friday. It is not this Friday. And
Same time, right?
yeah. And for the assignment 1, both the Gradescope and the Moodle links are open. Again, I apologize. Like for the second assignment, we will open it as soon as we release the assignment. So I also read a bunch of feedback in the Google form. So like one of the major comments is that assignment 1 was, the instructions in assignment 1 was a bit vague. So I will work on assignment 2 and make sure that it doesn't have imprecise instructions. But remember that there is a difference between instructions being vague and the questions being open-ended. So for example, when I ask you to do come up with a new way of like filling the missing values, it's an open question. So it's not the instruction being vague. And there was also another comment that the assignments are slightly longer than what was expected. So one reason for that is we don't have labs. So ideally, you are also supposed to utilize your lab times for the assignments. So the assignments cover both your weekly, bi-weekly lab time, which is 3 hours, and specific part in your like outside the class hours, like which you would normally use for the course assignment. So nevertheless, I think the second assignment is going to be shorter than the first. So maybe it would balance out. Is there anything else? Well, there is also another comment about the notes being, again, like too short, sometimes with a lack of, like sometimes jumping from one section to other section. As I mentioned before, this is the first iteration of the course. In the future, like I hope to improvise and expand on these notes. So sorry if there are any parts which is like not very clear, but instead of giving a general feedback, like if you can actually tell me which section of the notes is problematic, that is going to be a very useful feedback because I will work on those sections before the next offering of the course. So uh, I think that pretty much covers all the feedback that I received. So for a long time, people were asking me, when are we going to move from linear models? So we are going to take a step up from linear models in today's lecture. And we will start with what is known as generalized linear models. So we're still in linear setting, but like we're going to come up with a slightly richer class of models before we move to nonlinear models. Okay, so what are generalized linear models, right? So far, I think we have spent a lot of time in studying linear models, right? Like, so for example, let's take the case of linear regression. In the case of linear regression, like I had something like y of x is equal to w transpose x plus w0, right? So, okay, my iPad is not moving. Just give me a sec. Okay, sorry. Okay, so in the case of linear regression, like we had y of x is equal to w transpose x plus w0, right? So the y is usually a real number, and it was fine for regression simply because in regression the target is any real number, right? On the other hand, we also tried using the same model but for classification, and we had a lot of discussion, I think in a couple of lectures back, or in the previous lecture, I think in the previous lecture, where we discussed that there's no constraint on y in the case of classification, right? Like in the case of classification, let's say you're working on a binary classification problem where the output can be either 0 or 1. There's nothing constraining this y to be 0 or 1, right? On the other hand, like what we want ideally for classification, so we want models that can either directly predict these discrete 0, 1 labels, okay, or models which would, for example, give the posterior probability for the class, right? So the probability of ck given x, and this posterior probability would lie in the range of 0 to 1, right? So we want a model which could do this. So one way to do that is to take the same linear model, okay, and add an extra function, let's call it f, okay? So now this function f is going to be some nonlinear function which will constrain the output of the model to be something in between 0 and 1. Okay, so we are going to call this nonlinear function, which takes a linear model and squashes the output between 0 to 1, as activation function. Okay, so now let's take this new model that we have, which is y of x is equal to some function of w transpose x plus w0, right? So now I also mentioned that this is some nonlinear function, which is in the range of 0 to 1, right? So when I have nonlinear function on the top of the parameters, right? So now this model, this specific model, right, is no longer linear in the parameters. So this is not a linear model. Why is this not a linear model? Because the model is a function of, is some nonlinear function of the parameters w. Okay, so now this is not a linear model. Then what kind of model is this, right? Like, so how would the decision surface of this model look like? So maybe let's take a guess. So do you think this model can have a linear decision boundary or a nonlinear decision boundary? So I'm going to do a poll, a template poll. So A for linear decision boundary and B for nonlinear decision boundary. Okay, so I will stop the poll. 65% of you think this is going to have non-linear decision boundary. Okay, let's see if that is true. So let's look at what would be the equation for the decision surface. So the decision surface is usually something like y of x is equal to constant, right? So in the case of binary classification problem, when y of x is equal to 0.5, that is the dividing point for these two classes. So y of x is equal to constant is my decision function. It is basically f of w transpose x plus w0 is equal to constant. Okay, so now W transpose X plus W0, I'm just going to move the nonlinearity to the right-hand side. It becomes F inverse of constant. Okay. Now W transpose X plus W0 is equal to constant. Okay, so what is happening here? So the decision surface, even though the model is not linear with respect to its parameters, the decision surface is actually linear function of X, even if F is nonlinear. Okay, so these types of models are called as generalized linear models or GLMs. Okay, so GLMs have some complex analytical and computational properties than the normal linear models that we have seen. However, they are still relatively simpler when compared to the nonlinear models that we are going to see in the future. Okay, so is the idea clear? Like, so what we have done is, like, we took a linear model, we added a nonlinear function so that the model is squashed between 0 to 1. So now this is no longer a linear model, right? So remember that, like, if the model is okay, maybe let's try to compare this with the basis function trick that we did, right? Like, so in the case of basis function trick, we made the model non-linear with respect to X, right? So maybe let's try to understand the differences between basis function models and generalized linear models. So the usual linear model is y of X is equal to W transpose X plus W0, right? So if I go the basis function route, I would have a model like y of X is equal to W transpose phi of X plus W0. Remember? So this phi is a nonlinear basis function. Now in this case, you would actually have nonlinear decision boundaries. Okay. On the other hand, if you take the generalized linear model route, you have y of X is equal to f of W transpose X plus W0, where F is a nonlinear activation function. Okay, and this model will have linear decision boundary with respect to X. Okay, now you could combine both together, right? Like, so you could actually have basis functions added to generalized linear models, then you're going to again get nonlinear decision boundary. Okay, okay. So now this is the idea of generalized linear models. So in today's lecture, we are actually going to see one example algorithm in the class of probabilistic generative models. Okay. Remember that in the case of generative models, you would have basically try to estimate probability of X given Ck and probability of Ck, and then use Bayes' theorem, which is basically probability of, well, I will do it for 2 class setting, 3 and K class setting separately. So, but before that, like, P of X given Ck is known as class conditional density. Okay, and P of Ck is known as class priors. And what we will compute is P of Ck given X, right, which is the class posterior. Okay, so now let's see how to do this for a 2 class problem and then move to the K class setting. So in the case of 2 class problem, P of C1 given X, P of C1 given X is given by P of X given C1, P of C1 divided by P of X, right? This is the usual base rule. So now I can actually expand P of X. So this becomes P of X given C1, P of C1 divided by P of X given C1, P of C1 plus P of X given C2, P of C2. Okay, so I have just expanded P of X here. I'm going to do a little bit of simplification. So I just divide numerator and denominator by the numerator. So this becomes 1 by 1 plus P of X given C2, sorry, P of C2 divided by P of X given C1, P of C1. Okay, so now I'm going to add an exp and ln to this. So 1 plus, I'm going to do an exponential of minus ln P of X given C1, P of C1 divided by P of X given C2, P of C2. Okay, so I have just done a little bit of reformulation here because I'm trying to come up with a general formulation for this probability. So all I have done here is when you do X ln, they cancel each other. So I have reversed the fraction and put a minus in front, like, so they are exactly the same. Okay, so now I can actually write this as 1 by 1 plus X of minus A. Okay, where A is given by ln P of X given C1, P of C1 divided by P of X given C2, P of C2. Okay, so now this specific formulation has a standard name. So this 1 by 1 plus e power minus A is what is known as the sigmoid function. So this is sigma of A, where sigma is the sigmoid function. Okay, so sigma of A is given by 1 by 1 plus e power minus A. So this is also known as logistic sigmoid function. Okay, so what have I done here? So I have just reformulated P of C1 given X into a specific equation, which is sigma of A, where A is the ln of these two terms, right? So there is a reason why I kind of reformulated this posterior probability in terms of sigmoid. So sigmoid function, which we will see again and again in in this course, has several nice properties. Okay, so maybe let's spend a minute understanding this sigmoid function. So first of all, sigmoid is a squashing function. Okay, it is going to take the real line and squash it together, like to squash it in between 0 and 1. So the range for this function is 0 and 1. So the sigmoid will look something like this. Okay, and it has several other nice properties. Like, I'm just going to list those properties. We are going to use this in the future lectures. So one is the symmetry property. So sigma of minus A is actually equal to 1 minus sigma of A. I will leave this as an exercise for you to go verify. But this is a useful property. No. And the inverse of sigmoid, right? Which is basically A is equal to ln sigma by 1 minus sigma. Okay, so this inverse actually has a name. So this is known as the logit function. Okay, so what is logit function? If you know what is sigma. Sigma is basically the probability of C1 given X, right? And 1 minus sigma is probability of C2 given X. So this logit function is actually equivalent to ln probability of C1 given X divided by probability of C2 given X. Okay, so this is basically the log odds, the relative comparison between the two classes. Okay, I have just listed the properties here. Like we will use some of these properties in the future when we use sigmoid. But one thing that you should, like, if the one main takeaway from this discussion is when you want to compute the posterior P of C1 given X for a two-class problem, then that posterior has a form which is sigma of A, where A is some term, which is given here. Is that clear? Maybe I'll take questions here. Any questions? So any questions before we move to multi-class setting? Okay, repeat the last sentence. Okay, so the last sentence, okay, what I was saying is like when you have a two-class problem, the probability of C1 given X is can be formulated by using this sigmoid function, sigma of A, where A is the given term here, right? So, and the probability of C2 given X is given by 1 minus sigma. On sigmoid derivative saturate at 0 and 1. Yes, it will. So we will actually discuss this when we start talking about doing gradient descent with these models. It's a good point. Okay, so maybe we will continue. So now let's actually do the same steps, but for k greater than 2 classes. Okay, when you have more than 2 classes, let's say, like in that case, let's say I'm interested in computing probability of ck given x. Okay, now this is given by probability of x given ck, probability of ck divided by summation over j, where j is all the classes, p of x given cj, p of cj. Right? Now I could actually do a little bit of reformulations here and make this as exp of ak divided by summation over j, exp of aj, okay, where ak is given by ln. So ak is just the ln of this term, so that exp and ln cancels out each other. P of x given ck, p of ck. Okay, so if you substitute ak here, exp and ln will cancel each other and you get the first equation. Okay, so now this specific function, exp of ak by summation over j, exp of aj, right? In some sense, okay, maybe I'll use a different color. So in some sense, this is normalized exponential, right? So you have a bunch of exponentials and you're normalizing them. Okay, so now this will result in a multinomial distribution, similar to how sigmoid of A is going to give you like a simple like Bernoulli distribution. This is going to give you a multinomial distribution. Okay, so now this is actually a multi-class generalization of the logistic sigmoid function. Okay, and this function has its own name too. So we call this as softmax function. Okay, so why do we call this a softmax function? Because let's say there's one class which has close to 1 probability, and the rest of the classes then should have close to 0 probability, right? Like, so let's take a 3-class problem, and the first class is 0.99, second class is 0.005, third class is 0.005. I said this is the probability. Now, when you pass these values to the softmax function, you're going to get a peak of close to 1 for the first class. And okay, sorry, this is actually the output of the softmax, right? So softmax give you these probability values. So essentially what happens is, like, if there is one class which is the most probable, then that class peaks out, right? So in some sense, this is a very soft argmax, but we just call it a softmax function. So is that clear? Okay, so for like what have we done? Like, so in the case of 2-class problem, P of C1 given X is given by sigmoid of A, right? Is it A or minus A? Sigma of A, right? Where A has some equation, like we don't care about that right now. And for K class problem, okay, P of Ck given X is given by softmax of, let's just call that a whole A vector. Okay, softmax of A, and this is basically this function. So it's exp of ak divided by summation over j exp of aj, and this is 1 by 1 plus e power minus a. Is that clear? Okay, so now this is a very general formulation, right? So now we are going to use this formulation to come up with one specific implementation, which is Gaussian discriminant analysis. Okay, so we will discuss Gaussian discriminant analysis only in a two-class setting, I guess. Yeah, we are going to discuss it only in a two-class setting, and you could just extend this discussion to K classes. Okay, so GDA is essentially a probabilistic generative model with two major assumptions. Okay, so the first assumption is the class conditional densities P of xk given ck, right, or Gaussian. The second assumption that we are going to make is all classes share the same covariance matrix. Okay, so these two are actually strong assumptions. Like we are starting with these strong assumptions. Like the assumptions are P of xk given ck is Gaussian, and all the classes actually share the same covariance matrix. Okay, so we will first start with this restricted model, and then we will slowly remove both the assumptions and come up with the most general model. Yomna, you can ask your question.
What are those two assumptions in real life? What does it mean in real life?
Okay, so, well, that's a good question. So in real life, it means that, okay, first of all, Gaussian is one of the most common distributions, and like there is a lot of places where you would have a Gaussian assumption, which is also supported by law of large numbers, right? So in general, it is not a very bad assumption to assume that the class conditional densities are Gaussian, okay? But in real life, you would see situations or example data sets where that doesn't hold. So in that cases, this model is going to perform bad. Similarly, for example, the second assumption is even more restricted. It says that all the classes should have same covariance matrix, right? Like, so that need not be true. Like you might have different properties for different classes. So in real life, these are actually a bit restricted assumptions, but we will start with the simplest possible setting, like so that we can do, like we can develop the algorithm, and then like we will, I think in today's lecture, we would remove the second assumption, but probably in Monday's lecture, we will remove the first assumption. Is that fine?
Thank you.
Okay. Okay, so now I need to remind you guys about the PDF of the Gaussian distribution. So P of x given ck is for a multi-dimensional Gaussian. Like, so when I have d-dimensional Gaussian, is given by 1 over 2 pi power d by 2, 1 over the determinant square root, right? And x pof minus 1 by 2 x minus mu k transpose sigma inverse x minus mu k, right? So this is probably one of the most useful equations to remember. If you have seen Gaussian in different other courses, like, so you would know this already. But I think we will also have 1 week, specific week reading just on properties of Gaussians. So you could dig deeper into Gaussians. Okay, so just to tell the notations here, the mean is given by mu k, and the covariance is given by sigma, and the mod sigma actually means the determinant of sigma. Okay, so now let's consider the 2-class problem, as I said. Okay, so what is the formulation for 2-class problem? Probability of C1 given X is given by sigma of A, right? Where we actually had an equation for A, which is ln probability of X given C1 P of C1 divided by probability of X given C2 P of C2. Remember? Okay, so now let's actually split this further. So I'm just going to cut this and move it to the next page. Okay. 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 So now I can actually split this further into ln P of X given C1 divided by P of X given C2 plus ln P of C1 by P of C2. So this is just the basic properties of logarithm, right? Okay. So now let's consider the first term. So if you remember, what is P of X given C1? So it has these terms, right? The first term and the second term, they are common in both the classes. So they are going to cancel out. So all you have is just this exponential, right? So let's write that here. So it's going to become ln exponential of, okay, minus 1 by 2 X minus mu1 transpose sigma inverse X minus mu1, okay? You'll have another exponential in the division, divided by exponential of minus. So I could bring it up by just using the properties of exponentials and say simply plus 1 by 2 X minus mu2 transpose sigma inverse X minus mu2. Okay, I'm kind of skipping a couple of steps here. So you would normally write this as e power minus 1 by 2 first term divided by e power minus 1 by 2 second term, and then you bring the denominator to the numerator. Plus the second term is something where you can't do anything, so it's just ln of P of C1 by P of C2. Okay, so now we can actually expand this term so that things can be simplified. The first simplification is ln and exponential cancel each other, right? So you just have the rest of the terms. So I'm going to expand them. So I'm going to take minus 1 by 2 totally outside. Okay, so the first term becomes X transpose sigma inverse X. I have just multiplied the first with the middle and the first and the third, right? Similarly, minus X transpose sigma inverse mu1. Now let's go to the second term in the second part of the first term. So minus mu1 transpose sigma inverse X, right? Plus mu1 transpose sigma inverse mu1. So I have totally expanded the first term. Similarly, we are going to expand the second term, but since we took a minus 1 by 2 out, we are going to add minus to the whole equation. So it becomes minus X transpose sigma inverse X plus X transpose sigma inverse mu2 plus mu2 transpose sigma inverse X minus mu2 transpose sigma inverse mu2. It's exactly same as the first term except for mu2's and signs changed, okay? Plus ln P of C1 divided by P of C2. Okay. It is okay if you did not follow me exactly from the first step to the second step, like you could go back and work on it. But the most interesting thing that you should know is the terms which involves X square, right? The first term and the second, and this term and this term, they actually cancel each other, right? So what you have remaining is all equations in terms of x, right? So now I could actually, and they actually club together at some places, I guess. So for example, these two things club together and these two things club together, right? So when I bring the minus 1 by 2 inside, so this is going to become x transpose sigma inverse mu1 minus x transpose sigma inverse mu2, okay? Then minus 1 by 2 mu1 transpose sigma inverse mu1 plus 1 by 2 mu2 transpose sigma inverse mu2. Okay, so all I have done is brought the minus 1 by 2 inside and added things which could be added. Plus you also shall have ln p of c1 by p of c2. Okay, okay. So now, what are the terms which has x? These are the only two terms which has x, right? So now I can write this whole equation in terms of W transpose X plus W0. So I'm just going to take things which are with X together, sigma inverse mu1 minus mu2. Okay, then the rest as such. So minus 1 by 2 mu1 transpose sigma inverse mu1 plus 1 by 2 mu2 transpose sigma inverse mu2 plus ln P of C1 by P of C2. Okay, so now this whole equation looks like W transpose X plus W0, right? So you have this term which becomes W transpose and this whole term which becomes W0. Okay, so I'm just going to rewrite it in the next page. So we have W transpose X plus W. So we have similar formulation as the linear regression for GDA. Okay, so this is my GDA function. Okay. Is this y of x? No, this is just A, sorry. A can be treated as W transpose X plus W0 and P of C1 given X, to remind you, is still sigma of A. Okay, where W is given by sigma inverse mu1 minus mu2 and W0 is given by minus 1 by 2 mu1 transpose sigma inverse mu1 plus 1 by 2 mu2 transpose sigma inverse mu2 plus ln P of C1 divided by P of C2. Okay, and probability of C1 given X can be now written as sigmoid of W transpose X plus W0. So it's the same function, right? But we have different parameters. Okay, so now what are the things, what are the properties that you could tell about this GDA? First of all, there is no quadratic term. The quadratic term cancelled, right? So this model is a generalized linear model and the decision boundary is a linear function of X. Okay. Now, there is also another interesting aspect that you could say from these equations. You see that the prior probabilities, right, of the classes enter the system only through the bias. So the third observation is prior probabilities enter the system only through the bias. And we have already discussed like the role of the bias, right? So what is the role of the bias in decision boundary? So maybe can you guys type in the chat? What is the role of bias in the decision boundary? Okay, so it translates or shifts the decision boundary, right? So in some sense, the prior that you have can only shift the decision boundary, but the orientation of the decision boundary is actually learned from data. Okay, so that is what this means. Okay, now, yeah, okay. So here you can actually, wait, did I write in a reverse way? Okay, maybe. Okay, so here you can actually see in this figure, the class conditional density for two classes. Okay, so now this is class one, this is class two. So this is actually, okay, this is actually probability of x given c1. This is probability of x given c2. Okay, now when you do this Gaussian discriminant analysis, like you would get probability of c1 given x like this. So you can see that in the region where class one is highly probable, like your sigmoid is close to one. In the region where your second class is most probable, your sigmoid is actually close to zero. Is that clear? Okay, so now we have a new model, right? So which is y of x is given by sigma of w transpose x plus w0, right? Now this w and w0 are in turn given by these equations, right? So let me just cut these equations for our discussion. Okay. Okay, so now can someone tell me what are the parameters of this model? So we have a slightly fancier classifier, right? Like which has a nonlinear function to squash things to 0 to 1. But we need to learn the parameters of this model. So what are the parameters of these models? Chat, maybe? Okay, I'm waiting for your, well, W and W0 are the parameters when you just look at this equation, but they are not something that you're learning because they are indirectly given by some other equations, right? So what are those? So I think someone is saying the means and the covariance. Yeah, is there anything other than the mean and the covariance? Okay, there's definitely, okay, parameters. There is definitely the mean, mu1, mu2. There's definitely the covariance, sigma. Is there anything else that we need to learn from the data? The class prior, right? So P of, we don't know what is P of C1 and we don't know what is P of C2, right? So we need to learn these parameters from the data. So the next question is how to learn these parameters. Okay, so probably we cannot do that in this lecture, but I would still try to motivate for it in the given 5 minutes. So we need a way to learn these parameters, right? Like, so remember that in the case of simple linear model, you had a least square objective, right? Now in this case, we have a probability which is outputted by the model. So now probably we need to use a different objective function, right? Like so I have a model which gives out the probability. Now what kind of objective function can I use, right? Like so what, like, okay, what is the thing that I want to minimize or maximize? So what do you think would be a right objective function? So basically we are looking for some objective function. This objective function should take a model which is outputting P of C1 given X, right? And increase its performance. So how can we do that? Okay, proportion of good classifications. Okay, so we want to increase the good classification. So how can you tweak this model? Like, so what should you do to this model so that it produces right classification? Max what? Max what? Okay, yeah, we need to define a cost function. Okay, any ideas for how to do that? Okay, yeah, well, it's right. Like, so we need to, okay, so a standard way that we have seen so far is to define a cost function and minimize it, right? Another way in which we could do it here is, as someone answered, you could try to maximize the probabilities, right? So you maximize the chance that this model will give P of C1 is given x is equal to 1 when class is 1 and 0 when class is 0, right? So that is what we are going to do today. So now let's consider I have some data set, okay, which has a bunch of data points where n is equal to, I have n data points, okay? And out of these n examples, okay, so T of n is going to be 1 for class 1, class C1, let's say. T of n is equal to 0 for class C0. Okay, so now let P of C1, the prior probability of C1, right? Like we're going to call that as pi. Okay, then the probability of C2 is given by what? 1 minus pi. Okay, so now consider any data point. X. Okay, now what is the joint probability of xn comma C1? So what is the joint probability of this data point being class 1, right? So, well, no, that's a wrong English explanation. So let's just call it as joint probability of x and C1, okay? Now this is given by P of C1 multiplied by P of xn given C1, right? I have just applied the chain rule here. Now we know what is P of C1. P of C1 is pi. Now what is P of xn given C1? It's the Gaussian that we assumed, right? So this is basically a Gaussian, which is xn given mu1 and sigma, right? So this is P of xn comma C1. Similarly, P of xn comma C2 is going to be probability of C2, which is 1 minus pi, okay? And the Gaussian, which is xn, which is centered around mu2 comma sigma, okay? So now I'm going to define what I call as the likelihood of a data point xn comma tn. So what is the likelihood for any random data point xn comma tn? So the likelihood is this term if it comes from class 1, sorry, this term if it comes from class 1 and this term if it comes from class 2, right? So I can write this whole thing together as it's the first form, okay, if it comes from class 1. So I'm going to do it like this, okay, and 1 minus pi times normal of xn given mu2 sigma inverse, sorry, we don't need the inverse, power 1 minus tn. Okay, is that clear? So whenever the data point belongs to class 1, then the second term becomes 0, it is just the first term. Whenever the data point belongs to class 2, then the first term goes to 0, it's only the second term. Okay, now this is the likelihood for one data point. Now my objective function, I will just define the objective function and we will stop. So my objective function is going to be maximize the likelihood for all the examples in my training set. Okay, so how to do this, we are going to see that in the next lecture. But just to give you an idea, like a rough idea of like what we have seen so far, like, so we are looking at probabilistic models And specifically, we are interested in a generative model which will try to model P of X given C1, CK and P of CK, and use Bayes rule to compute P of CK given X, right? So now we started with two strong assumptions that the class conditionals are going to be Gaussians, where even the covariance matrices are shared. The advantage of sharing covariance matrices is like you have a system where there is no X square term, right? And for such a system, we actually formulated the model, right? And this is how the model looks like. So once we have the model, the next question is how to learn the parameters, right? So to learn parameters of a simple non-probabilistic linear model, we used least squares, which is try to minimize the error, like the gap between the predictions. But now we are going to, now we are looking at a second type of objective function, which is maximum likelihood objective function. So in this case, instead of trying to minimize a cost, we are maximizing the likelihood of your data points. So if I have a system which is going to give high probability to all the training data, then I could assume that such a system has fitted the data very well, that it could help us in generalizing to test examples. Okay, so well, I'm sorry, I'm kind of cutting the algorithm in the middle, but we will go through the objective maximization process in the next lecture. Okay, did I summarize? I summarized before seeing Ali's comment. I hope the summary is good. So is there any questions? I will take a couple of questions and then stop the recording. Gabriel?
Hi.
Hey.
Yes, my question, can you go back to the values of the W vector that you computed for this algorithm?
Yes.
I was just wondering, it's pretty similar to the one we had with the Fisher linear discriminant, because we had like the inverse of a covariance matrix times the differences in the means. But instead of sigma, it was like SB or something like that.
Yes. Oh, well.
Is there like a connection between the two techniques?
Okay, so they are both discriminant-based approaches, right?
Mm-hmm.
So in fact, okay, your confusion is valid. In fact,
not confusion is just like a realization. I'm wondering if there's like an intrinsic relationship.
Yeah. Okay, so there is a relationship between these two models, and in fact, most of the textbooks would actually introduce GDA as LDA. So there's a lot of confusion. I try to avoid that confusion by just naming this as GDA, but some textbooks also introduce this algorithm as LDA. So that confuses between GDA and the Fisher's LDA. But you are right that there is a lot of resemblance. But remember that LDA is used only to come up with the direction, not with the classifier. On the other hand, GDA is much more mature approach because here it also gives you the classifier.
Yeah. Well, for LDA, we had to choose a
threshold
to discriminate, but in that case, it's like the W0 plays the role of the theta, like it gives.
Well, it's not just the W0. So that's actually a good way to look at it. Yeah.
Well, okay, I was just wondering, so thank you.
Okay.
Yep.
Any other questions? It would be useful, like if you guys quickly revise today's lecture before the next lecture, simply because we stopped in the middle. But I will also give a quick recap when we start next week. Any other questions? If there is no more questions, I'm going to stop the recording. Thank you.